Good evening, Germantown scholars. So let's finish up our discussion about the Bohr model. Okay, let's finish up our discussion about the Bohr model. All right, so let's review some things. And this is not so much, I know y'all, some of y'all had physical science. Hopefully y'all went through some work, okay, in this. Let me go ahead and change this view here real quick. And let's go ahead and erase those real quick. Use my fingers. No, eraser. All right, so some phenomenal light, and this sort of builds on what we're doing, so we'll just mention this, just take them at face value. Ampere's law states that a current caused by an electric field generates a magnetic field. Now, Faraday's law states this. Faraday's law states that a changing magnetic field generates an electric current. Okay? So together, these two laws, what they tell us is that a changing electric field would create a changing magnetic field, which in turn would create a changing electric field, which would create a changing magnetic field, and so on and so forth. Now, these time-varying fields are what we call electromagnetic waves. So, and this is how we describe our waves. The electric and magnetic wave segments of this wave, electromagnetic wave, they're perpendicular to each other, all right? They're at a 90-degree angle, and they go in the direction of the propagation of the wave. Now, wavelength is how long that wave is in meters. Frequency is the number of waves in a second. Okay? So, let's explore these further. This is an example of how the electromagnetic wave is created. Now, if we're listening to an FM radio station, or we're getting a cell signal, or what have you, or a TV broadcast, that's going to be oriented along the vertical or the z-axis. The electrons, they get accelerated up and down by the changing voltage. And as the electrons accelerate, they create a changing electric field in the z direction. Now, this creates a magnetic field, a changing magnetic field, in the XY plane. You can see as the wavelength, as the electron goes up, you're changing the magnetic field on the XY axis. So, these initial magnetic and electric fields, they'll propagate to the right along that y-axis, and they're going to get very small very quickly due to the 1 over the radius squared and 1r dependence. But because these are changing fields, they keep creating their partner field. Now, this creates an electromagnetic wave which will keep going and going and going until it gets absorbed by some other material, like a wall. Now, again, just for fun, the solution to Maxwell's equations show that the speed of an electromagnetic wave is 3 times 10 to the 8th meters per second. This was also measured to be the speed of light. So, we realize that light is an electromagnetic wave. So you got some interesting relationships between the electrical permittivity and the magnetic permeability constants. And that's what they are. If you multiply those together, guess what you get? 3 times 10 to the 8th meters per second, the speed of light in a vacuum. So right around the same time that the Bohr model was being developed, Einstein and others developed a particle theory of light. Now, in this theory, light is emitted as a massless particle called a photon. Now, each photon, though it is massless, carries a specific amount of energy. So the energy of the photon is given by this formula. Energy equals H, which is a constant. We call it Planck's constant. and it's always equal to 4.14 times 10 to the minus 15th electron volts per second. Now, another way of saying this, if we wanted to say it in joules, Planck's constant in joules is, let me go ahead and switch that, is 6.63 times 10 to the minus 34th, 10 to the minus 34th joules. Okay, seconds. Now, F is what we use for the frequency of the light in hertz. Now, a hertz is equal to 1 over seconds, or S to the minus 1, a reciprocal second. So, going on. Waves are given this formula. Speed of light equals lambda, or the wavelength, times the frequency. So we can move this around, all right, and put frequency equals C over F, or C over lambda, or wavelength. Now we can use this formula to find the energy of a light at a given wavelength. So again, we have H, or Planck's constant, is equal to 4.14 times 10 to the minus 15 electron volts per second, or seconds. And the speed of light is equal to 3 times 10 to the 8th meters per second. So lambda is the wavelength of light in meters. So we can sub this in, right? We can sub that in for F. And when we do, we have E equals Planck's constant times the speed of light, which we know, divided by lambda. So remember from our last little video, the photon from the second energy orbit to the ground state emitted 10.2 electron volts. So if we put this into our formula and we're trying to find our frequency, all right, E equal HF, we're looking for F. So we take that energy from that photon, 10.2 electron volts, and we divide it by Planck's constant, which is a given, and we get 2.5 times 10 to the 15th hertz. So we can take that and put it into our wavelength formula, because we know the speed of light, and we can find the wavelength. And the wavelength would be speed of light divided by the frequency. And we get 1.2 times 10 to the minus 7th meters. Now, if we were to convert that to nanometers, all right, we divide through by 1 times 10 to the minus 9th, okay? And we get 120 nanometers. Guess what? This frequency is right along the Lyman series in the ultraviolet, which we can't see. See, it'd be about 120 nanometers. Every one of these, right, on the Lyman series, if we were to take this, the energy of the photon going from 3 to 1 or 5 to 1 lines up, if we put that in the formula, with every one of these lines. If we were to take the Balmer series, okay, and again, that started at 2, 1 over 2 squared, then 1 over n squared. And if we were to take that energy loss, or the photon, the energy of that photon, and go from N3 down to N2, that'd be what, 1.151 minus 3.4, or 3.4 minus 1.51. You're going to get what? You're going to get 1.89. And if we were to run those through our formulas, all right, now you're going to go right along the Balmer series as far as the wavelength. So the energy that released is smaller than in transition to the ground state. So the frequency of the emitted light is lower and the wavelength is longer. Passion series, same thing. All right, you're going down to N3. So these photons, or these electrons, are moving from 4 to 3, 5 to 3, 6 to 3, and so on and so forth. All right, now you can see that the energy release is smaller than when you go down to the ground state. or to the N2 level. So this is the lowest frequency of light, and it'll have the longest wavelength, which means we're in the infrared region. So the spectrum of light, being made up of lines of a specific color, is explained as being due to the release of the specific energy when that electron will move to the lower energy level. So, according to Bohr, N stands for what? Pause. The energy level of the orbit. Now, in the Bohr model of the atom, an electron in its lowest energy state, okay, is what? Closest to the nucleus or furthest from the nucleus? Pause, of course, is closest to the nucleus. Which of the following best explains why atoms produce light of only specific colors, not all colors? They don't contain enough electrons? Are electrons constantly radiating light? Pause, see what you can think. Of course, the answer is electrons only radiate light when moving between these specific energy levels. Which of the following best explains why excited atoms produce emission spectra and not continuous spectra? Pause. If you look at all these, the answer has to be electrons can only exist in certain stable orbitals of specific energy. So we'll do this a little bit. So this electron can take a number of routes back to its ground state. It doesn't always go from N4 down to N1. It could, and it does, but that electron can go from N3 down to N1, or it can go from N3 down to N2, then down to N1, or it can go from N4 down to N3, down to N2, down to N1, or it can go from N4 down to N2, down. You see what I'm saying? So here you see two separate paths. That electron is going down from the third energy level. This side is going down to N2, then it goes down to N1. And it's going to produce two lower frequency photons. All right. This one on the right is only going to produce one higher frequency proton. So, hydrogen atoms are easier to understand because there's only one proton and one electron. So its emission spectrum shows all the different possible wavelengths of visible light that's emitted when the excited electrons will return to the lower energy state. So here we have this one is going down from energy level 3 to energy level 2, and we get 656 nanometers, or red on the spectra. This one is moving down from energy level 4 to energy level 2. And there we can see that light blue are 486 nanometers. Now this purple, almost ultraviolet, we're going down from 6 down to 2. And that's going to be a longer wavelength, all right? And lower energy, okay? So let's answer these questions and then we'll go to our next video. Which of the following electron transition will produce the higher energy spectral line? Take a break, pause. And if you think about it, the little chart looks like so, ground state. This is going to produce the most energy, going from like 2 to 1. Anything going into the ground state is going to produce the most energy because of that big gap there. So it would be 2 to 1. So let's take a break, then we'll come back and we'll start on this one. Okay, so let's break this up. This is Coach Scott, and This would be, I guess, Bohr Model 3A. Okay, and we'll come back to the video and I'll make another one and we'll do some of this harder math.